Work, right? Yeah, cool. Hello everyone, so welcome to the Astronomy on Tap today. So today I'm going to talk about something that is a little bit too loud, I don't know. So I'm going to talk about something about the creation of the first elements in the universe, and then, but that'll be at the very end of my talk. First I'm going to try to give a small background information about what we know about the universe, and then how we got into the place of trying to understand where we all come from. So for thousands of years, people have been wandering, looking at the night sky to see and to answer one of the most profound questions in human thinking, and that is to understand why we all are here. So you look at the night sky and you wonder if there's an edge to it. Is the universe infinite? Or is there an edge to it? Can you put the hand outside the edge of the universe? What is there? What are the small blinking dots in the night sky? And do they live forever? Do they die? We did not know, right? So from the ancient Australians to the Vikings in the north, from the Chinese to the Native Americans, everyone had their own creation story. And some of them went around similar to the cosmic egg kind of a principle, thinking about the universe in a different way. Then we had the Greeks coming with their own systems of the universe, where we put the Earth in the middle of the universe, and everything around circling around us. Then of course in the 1500s, Copernicus and Galileo kind of revolutionized the idea that we are not actually in the center of the universe, we are not in a special place, and everything is not revolving around us. So kind of an idea that we are not actually special much. Of course, later on, only in the, when it clicks sometime, nope. Yeah, so not until the early 20th century that Einstein brought the ideas together on a concept called space and time to try to explain the universe in a more mathematical format. And he came out with these equations and figured out from the math that he cannot really bring a stable solution to the universe to make it static. But there was no observational evidence to suggest that the universe was actually not static. So he made up a random number, like a number, and put it into it to make the universe stable. But later on, two people, a Belgian priest, Georges Lamarthe, and Edwin Hubble from the United States, they found out that something fascinating about the universe, which kind of changed our whole view of the universe in certain ways. What they found out was can simply be put something like this. If you measure, so this is a plot of speed against distance. So what they did was they measured the distance to objects in the sky and then figure out how fast they're moving. So what they found out was that the further away things are, they seem to be going at very high speeds, in increasingly high speeds. That means everything is kind of moving away with each other. So this kind of changed our view of the universe in a certain way, that we realized that the universe is not static, but it might be expanding in some ways. So this brings out to a question, if everything is moving away from us, how fast is this going? So this is kind of a interesting question, because this kind of tells you the speed of the expansion of the universe. So do we know the answer to this ultimate question? I hope you can hear this.
Yes, but you're not going to like it. All right. The answer to the ultimate question of life, the universe, and everything is 42. Yes, I will.
Thank you, Liz. So the actual answer is that everything is moving away at 42 miles per second per 3 million light years. All right, so there is a 42 in it. So what it actually means is that if I stay from Earth, I go a distance of 3 million light years. Everything there is moving at a speed of 42 miles per second relative to Earth. If I go 6 million light years, everything there is moving 84 miles per second. So it's not very fast, but it's actually moving quite fast in relative terms of, for understanding. So this kind of gave rise to an increasing concept. If everything is moving away from us, at some point in time, we could bring everything back together and they'll be touching each other, right? It'll be like this dense thing that everything that you see in the universe would be in this space, because if everything is moving away from each other, you can bring them together. And this kind of gave rise to the new idea of the universe in the 1900s that is famously called the Big Bang Theory. So the mathematical framework was developed on top of Einstein's general relativity equations by Alexander Friedmann and William D. Sitter, a Russian and a Dutch mathematicians. And it was a novel solution for to understand the universe in a way to explain the observables. And so people are really skeptical about this idea for a while. But there was one nice prediction that was made by this theory, which was later accidentally found in the 1960s, which is called the cosmic microwave background. So this is the furthest light in the universe that you will ever see. And it is the remnants of the Big Bang. So soon after the Big Bang, the universe was cooling. And this is the light that kind of reflects what was there just about almost 400,000 years after the Big Bang. And our next speaker will, of course, tell more about how we can observe them in the most coldest places in the universe. But there were certain issues with the Big Bang theory. The one thing was that this is a figure that actually shows hot and cold. So this is like a temperature map of the universe, the whole sky. But even though you can see the temperatures fluctuate quite a bit with colors, the scale is 1 over 100,000. So the changes of temperature is very, very, very small. In most cases, the temperature is almost uniform in this whole image. This means that if I look to my left or right, I look further away, the furthest distance I can see, at 45 million light years away, I see a patch of the sky, and it has the same temperature as if I look to the right side of my hand, like if I look further away, another 45 million light years away. But the problem is, these 2 points in the universe are 90 million light years away in distance. But if the universe was only, I meant billion, I was talking wrong, billion, okay? So, and if the universe was only expanding for 13.1 billion years, 13 billion years, there was no way that these 2 points in the two sides were together at any point of time. This means that there is no way that the temperature can be the same in these two parts, because they have not communicated with each other to actually get the temperatures correctly. So this cannot be explained for a while. So then the astronomers came up, the mathematicians came up with a solution for the Big Bang. It was kind of an add-on to these things, like, you know, buy a game and then you have an add-on packs that you can buy on to that. So inflation was kind of plugged into the Big Bang theory to make it kind of work. What it kind of meant was that at certain point in time, the universe started to expand in a very, very high speed, in exponential speeds. The universe grew from like a small piece of size of an atom to almost like of a blood orange within a very, very short time period. And we have a lower limit to this, and that afterwards that gave rise to this thing called the Big Bang, and which kind of explained afterwards using the normal physics that we had before. But this kind of gave rise to interesting conundrums as well that we could not explain easily. So one thing is that we don't know how long this inflation happened for. We have a lower limit because from the observables that we have, we know it has to happen for around at least 10 to the minus 35 seconds. So that's the lower limit. But it can have happened for 1 second. It can have happened for 10 minutes. It can have been happening for like 1,000,000 years. It can have been happening for an infinitely long time. And if you think about that, the universe that we cannot see might be like infinite in extent. We will never know how big it is in this kind of framework. The second thing is that, if it clicks, the energy that kind of drew this Big Bang, which is called the inflatron field, is kind of an interesting field. Mathematically, it's a very, very efficient process, and it will never quite finish when it actually gives rise to our universe through the Big Bang, and there's so much energy left over. So there are mathematical theories that says that there is a Big Bang after a Big Bang after a Big Bang happening like thousands and millions of times. Does it mean that there are multiple universes from this theory? We don't know. But only thing what we know is our own universe, which we can observe. And for that, we have a relatively good timeline. And we know what happened and how the evolution of ourselves, the universe that we see, kind of drew upon. So we know that we started in the Big Bang, something happened, we don't know what happened, no one knows what happened at the location of the Big Bang, when it happened or anything like that. We know what happened soon after that, and we can explain almost everything that came afterwards. So you can see the faint glow of the cosmic microwave background that I showed you. It's about almost 400,000 years after the Big Bang. Then the first stars, the first galaxies started to form, and then our galaxy formed, and then there was life at a certain point. So to explain what happened, it's interesting to go and look back how these atoms were created just after the Big Bang. So this kind of a small video that I found on the internet, which kind of explains this in a nice way. In the beginning, there was a dense point in the universe, which was really hot and dense. And then it kind of, oh, it's not working. All right, yeah. So at a certain point, it was there was this energy which was really, really hot and dense, and all the energy was all together. We call it a super force, and the matter and everything was together. There was no way of identifying things, matter and energy from each other. They were in such a way. And at a certain point in time, the gravity field will go away from it, and then so will the strong force. So once these two forces kind of go away from each other, we call it decoupling in certain ways. This gave rise to this thing that we call the inflation. That expanded the universe in a very, very fast way. And it started to expand up to a certain level. And then that energy that expanded the universe kind of cooled down in a way, and that led to the universe cooling at a certain point. After that, the electromagnetic energy and the weak force decoupled from each other, and that gave rise to the production of the first subatomic particles in the universe, that we call them the quarks. And these quarks and the leptons that were created after on, which also you can observe that from what you will hear from later on the talk, kind of told us the story of how the first atoms might have formed. To explain the story, I kind of wrote some balloons here which might make it easy. So in the beginning, it was really, really hot. So everything was moving away very fast. So imagine this to be a proton, and imagine this to be a neutron. So what happened was the neutrons were formed first, and then the protons were formed afterwards. And then they started colliding. Nothing happened because it was so hot. And at a certain point, the universe was expanded well enough that the protons and neutrons stuck together to make the deuterium. And then you will start getting more and more of deuterium, right? But if this process happened in a way that I describe now, it's going to bring all the deuterium together, all the hydrogen will get fused into heavy elements. The problem was the universe was so hot that when the deuterium, this element was made, the energy would come and break this thing easily, and again you will have two different particles again. But at a certain point, the temperature cooled down well enough that the deuterium became stable, and then you could have two deuterium. So it's like one proton, one neutron, one proton, one neutron coming together to form the first element in certain ways, or after hydrogen, helium, to be produced in the universe. So and the universe was still hot, right? So what could have happened is that there could be more protons coming and try to stick to make lithium and other things. But the universe cooled down very quickly soon after that there was not enough energy to start producing anything higher than helium at this point. So this is the reason why, like, soon after the Big Bang, 75% of the universe was hydrogen, so it was just like one proton. flying around, maybe with a neutron when it's reionized, and then 25% was almost helium, and there was a little bit of lithium left, but we can safely ignore that. And so these were the first two elements that were created in the universe. But then, of course, we know that there has a whole periodic table of elements, and how were they created? So what you had was these massive hydrogen gas clouds that existed after the Big Bang, because there was a lot of hydrogen left over, and from the gravity they started collapsing, as you see from this video. So this is like all hydrogen cloud collapsing, and once the collapsing happens, the density increases. That means the temperature also increases, and you can see this kind of give rise to something that we call a protostellar core, which will end up becoming a star. And these stars will be the next building blocks of the universe to make the other things. So you can see the stars getting formed here, and so these are the small dots. So this is an artist's impression of how the early universe could have been with the first generation of stars. We call them population 3 stars. So there were no metals in them. They're made out of purely of hydrogen, helium, which is what was left over from the Big Bang. And you can see these stars are around these very strong neutral gas regions around them, because this is soon after the Big Bang. So like there's so much exotic physics going around here. And what you could do is now, if I take a human being, we can now trace back and see up to what amount of us is actually made out after the Big Bang. And you can see almost 10% of our human body is actually made from the things that were created in the Big Bang. So you go 13 billion years ago, something happened that we don't really fully understand, and that led to producing like 10% of our human body, and it's also created the first generation of stars, etc., which created the remaining parts of the periodic table. That's of course a story for another time, and in the remaining 1 minute so I'll quickly explain how we try to find this. This kind of related to star science I do a little bit. So you have these regions of gas clouds which are like without metals and with only of hydrogen and helium. And because these stars are really, really hot, they make a lot of energy that doesn't get cooled easily. So